Imagine navigating a maze where every turn could lead to a beauty or chaos. Sounds intriguing, right? Well, that's exactly what we are going to explore today. We are tackling a challenge that's all about finding beautiful paths in a graph. Get ready for some mind bending logic and a few aha moments as we decode this magical adventure together. Alright, let's dive into the core of our problem solving solution journey where we'll explore how to tackle finding the minimum penalty on a path through a graph. First, picture this. We are working with a graph made up of nodes and edges. Each node represents a point in our graph and each edge has an associated cost. Our goal is to navigate from the starting node to a destination node while incurring the least penalty possible. But what exactly do we mean by penalty? In this context, it's the cumulative cost we gather as we traverse from the start to the end. Now, to start, we need to gather some essential information about the graph. We read in the number of nodes and edges. This is crucial because it helps us to understand the size and complexity of the graph we are dealing with. Once we have that, we can begin to construct our graph structures. Next, we initialize our graph. We use a dictionary where each node points to a list of its neighboring nodes along with the cost associated with the edges connecting them. This structure makes it easy to look up which nodes are connected and what are their respective costs. What are the respective costs? Setting this up perfectly for the traversal we're about to perform. And after we have our graph set up, we'll read the edges. Once we look through the number of edges, and for each edge, we extract the two connected nodes and the cost between them. We then update our graph by adding these connections both ways. Since our graph is likely unidirected, this means if node A connects to node B, we also need to ensure that node B knows that it can reach to node A as well. Once our graph is fully constructed, we need to determine our starting and ending nodes. This is key because it gives us the specific points between which we'll be calculating our minimum penalty. Now here's where it gets interesting. We use a breadth-first search or BFS to explore the graph. Why BFS? Well, it's particularly effective for finding the shortest path in terms of the number of edges, and in our case, we can adapt it to consider it as penalties. We initialize a queue to help us traverse through the node systematically, starting from the start node with a penalty of 0. And as we dequeue nodes, we check if we have reached our destination. If we have, we simply return the current penalty as that's our goal. And if we haven't, we look through the neighboring nodes. For each neighbor, we calculate a minimum potential penalty by combining the current penalty with the total cost of the edge leading to that neighbor. This is where magic happens. Using a bitwise OR operation allows us to keep track of the penalties efficiently. Before we enqueue this neighbor for further exploration, we check if we have already visited this neighbor with the new penalty. This is crucial to avoid cycles and unnecessary computations. If we haven't visited it yet, we mark it as visited and add it to our queue. If we finished exploring all possible paths and don't reach the end node, we return -1, indicating that the destination is unreachable. So to recap, we build a graph from the input, set up a BFS to explore while tracking penalties, and employed a smart way to ensure that we aren't revisiting nodes unnecessarily. This method lays the groundwork for our function to find the minimum penalty path effectively. We tackled an intriguing problem from HackerRank where we needed to find the minimum penalty paths between two nodes in a graph. We kick things off by setting up our graph using a dictionary to map each node to its edges and associated costs. After reading the number of nodes and edges, we populated the graph and then used the BFS breadth-first algorithm to explore possible paths. The key takeaway here is how we handle penalties using the bitwise OR operation to track cumulative cost while ensuring each node was only visited with unique penalties. And remember, the real power of a solution lies in efficiently managing the graph traversal and penalty calculation. If you have found this video helpful, make sure to check out the link in the description below, and don't forget to give it a thumbs up and subscribe for more engaging coding challenge and solution. But wait, there is more. In our upcoming videos, we'll dive deeper into graph theories, exploring algorithms like Dijkstra and HackerRank for even more complex scenarios. So stay tuned and keep building those coding skills together.